recording. If you can put it into full screen, please.
Yeah.
Okay, so it's a great pleasure to have our own Apoorv Tiwari from Niels Bohr. And we'll talk about fermionic non-invertible symmetries in 1+1D. Take it away.
Okay. Hello, everyone. Thanks for the introduction, Sakura, and thanks for having me here. Today, I'll talk about fermionic non-invertible symmetries in 1+1D. And this is based on a recent paper that we put out on the archive last month with Lakshya Bharadwaj and Kansei Namura. If you're interested in this subject, you should also maybe look at these other works. There was a coordinated paper by Shengjie on a very complementary approach to the same subject, and also a paper a few weeks earlier by Wen, Ye, and Potter, which also took a complementary approach, but focused on invertible abelian symmetries. So as we are all well aware, generalized, in particular non-invertible symmetries have become a very active area of research. And part of the reason for this is these symmetries provide a new way, qualitatively new ways to organize states and operators in a quantum system. And therefore, they constrain infrared or low energy physics. So they can inform what kind of phases and transitions might arise in a system. They also have interesting connections to quantum information and mathematical physics. However, most of the focus related to these symmetries has been on finite symmetries in bosonic systems. And there's been a lot of work fleshing out, in particular in low dimensions in 1+1D, extensions of the Landau paradigm that incorporate these symmetries that has been now coined as a generalized or categorical Landau framework. There are many generalizations of this that are possible. For example, one can look at finite or continuous symmetries. Also, most of the work has been on generalizations of unitary groups. One can also look at how anti-unitary symmetries like time reversal or reflection get generalized or in the sense of categorical symmetries. However, in this work, I'll focus on generalizing bosonic to fermionic systems, which are, of course, of relevance. And I'll be focusing only on 1+1 dimensions. And I will also, I'll try to systematically understand what kinds of charges, phases, and transitions can arise in systems with fermionic non-invertible symmetries. To do so, I'll use a symmetry TFT-based approach. And symmetry TFTs have become one of the main tools in studying these problems in bosonic systems, and we'll study an extension to fermionic symmetries. So the plan is as follows. I'll start by describing what fermionic symmetries are, specifically in 1D or 1+1D. And then I'll describe fermionization and bosonization, which will play an important role in what follows. After that, I'll describe a fermionic symmetry TFT or symmetry TFT for fermionic symmetries and use that to understand the structure of generalized charges, phases, and transitions in systems with such symmetries. Of course, please feel free to interrupt me at any point if you have any questions. So what are fermionic symmetries? In 1+1D, a fermionic symmetry, here denoted as SF, is described by a fusion pi supercategory with a choice of fermion parity. So there are three layers of structure here in these three colors. The first is a fusion supercategory. Second is a pi structure. And the third is a choice of fermion parity. So let me one by one describe these three things. A fusion supercategory is a fusion category where the objects have a Z2 grading on them. Sorry, the morphisms have a Z2 grading on them, where zero graded object is bosonic, a morphism is bosonic, while a one graded morphism is fermionic. This further divides the kinds of simple objects that one can have into two classes, which are M-type and Q-type. Any simple object has a one-dimensional space of bosonic endomorphisms. However, depending on whether or not one has a fermionic endomorphism, denoted by 0 or 1 on the right side of this bar, the object is M-type or Q-type. And the Z2 grading has to be compatible with fusion. So if you take, say, two morphisms on a line and compose them, or two lines with morphisms on them and fuse the lines, then the fused morphisms have a Z2 grading, which is the sum of the morphisms that were fused. Local operators satisfy kind of fermionic anti-commutation relation. So if I have two morphisms or local operators, F and G, and I exchange the order in which they're implemented, it implements an isomorphism, which is given by the sign, which is -1 to the power of the Z2 grading of these two morphisms. Additionally, as in usual fusion categories, there are associators. However, these associators have to satisfy a variant of the pentagon equation, which is the fermionic pentagon equation. It looks much like the bosonic one, except there's this extra isomorphism, which is implemented when you move the F morphism across the G. So you pick up this sign. And the super pentagon equation has this form. So these are fermionic fusion supercategories. The next layer of structure is called the pi structure. And this just refers to the existence of a certain topological line, which I'm going to call pi. In the language of this paper, this is a theta defect. So this is just the insertion of a 0 plus 1D invertible fermionic theory along some locus on the space-time manifold. And this invertible theory is a Majorana fermion. Notably, this pi line is fermionically isomorphic to the identity. So there's a topological local operator which can implement an isomorphism between the pi line and the identity line. There's no bosonic isomorphism between pi and the identity. That's why we treat pi and 1 as distinct objects. And the third layer of structure is a choice of fermion parity. This is self-explanatory. However, so essentially one has to choose some object in the category that implements the grading. So if you link this line with a morphism, then you pick up a sign, which is the grading of the morphism. And notably, it has to have a certain junction, a property of crossing with the pi line, because the end of the pi line is fermionic. The linking of the fermion parity line should be -1 on the pi line. And this amounts to the fact that if we split the pi line on the fermion parity line, it costs a sign. This also implies that if you take if the fermion parity operator ends, in other words, there's a twisted operator in the fermion parity twisted sector. This could be topological or non-topological. The linking of this operator with the pi line is -1. Now, given some fusion category, a super fusion category with all this data and a certain choice of fermion parity, one can always define another category where the line that implements fermion parity is exchanged with pi times that line. And this corresponds to stacking the Apoorv invertible TQFT on the theory that we are studying. Since the Apoorv will play an important role, let me quickly describe what this is. This Apoorv is an invertible 2D theory. From a condensed matter perspective, it describes the infrared physics of the Kitaev chain in the topological phase. And essentially, the defining property of the Apoorv theory is that in the fermion parity twisted sector, or R sector, you have a fermionic odd operator. Or from a condensed matter perspective, there's a fermion odd ground state in the R sector, or fermion twisted sector. And therefore, this fermion parity operator is implemented by the pi line, and pasting it just amounts to changing the fermion parity by a factor of pi. So are there any questions at this point? Okay, if not, I'll move on to describing bosonization and fermionization. So all the fermionic symmetries that I'll be considering would have a non-anomalous Z2 fermionic symmetry. In general, one can also have an anomalous fermion parity, which corresponds to theories that also come with gravitational anomalies, so they can't be regularized on a lattice. However, for the purpose of this talk, we always restrict to non-anomalous fermion parity, and such symmetry categories can be bosonized. Or conversely, starting from a bosonic theory that has some symmetry described by fusion category S that has a Z2 subsymmetry, one can fermionize the Z2 subsymmetry generated by P here in order to generate a fermionic symmetry category. How this is carried out is follows. We start with the bosonic theory, stack it with Apoorv. One can always stack any bosonic theory and make it fermionic by declaring the fermion parity to be implemented either trivially by the identity line or by the pi line. And then once we do that, we gauge pi p. And upon gauging pi p, there's a dual Z2 symmetry. This is just bosonic gauging. And I'm going to call this dual symmetry generator eta. And then one identifies in the dual theory the fermionic parity to be pi eta. Here we could also identify it to be eta, but that's just a different choice, which would be up to stacking of the Apoorv theory, as I mentioned. So it's useful to see how the sectors, states and operators map under such a fermionization. But to do so, let's just quickly recall how states and operators map under Z2 gauging. Let's say we just have a Z2 symmetry, gauge it. There's a dual symmetry, T dual, which has a dual Z2 symmetry generated by eta. And the way the states and operators map, so there's a local uncharged operator, which maps to the trivial local uncharged operator. Twisted sector maps to the charged sector maps to twisted sector, and charged twisted maps to charged twisted. If you're more familiar with lattice systems, you can think of a 1D chain of two-dimensional local Hilbert spaces, and the Z2 symmetry is implemented by spin flip, so some product of sigma x's. And there we're familiar from Kramer-Warnier duality that single sigma z maps to a string of sigma x's in the dual Kramer-Warnier dual representation. That's what this encodes. Conversely, if you take a product of sigma x's, it maps to a single sigma z, which is charged under the dual Z2 symmetry. So this is nothing unfamiliar. Under fermionization, following the recipe I just described on the previous slide, one can study the mapping of sectors. I'm going to sometimes call the NS sector as the untwisted sector and the R sector as fermion parity twisted sector. This is convention from conformal field theory or string theory. Fermionization rules as follows. An untwisted charge sector boson maps to a R sector fermion. A twisted sector operator maps to a R sector boson, and twisted charged maps to a NS sector fermion. Let's see how these follow from the recipe I described earlier. So this rule number 2, if you start from a charged operator, which is charged under P, it's also charged under pi P. And we know a charged operator gets mapped to a twisted sector operator. So this is eta twisted. But since we identify pi eta to be the fermion parity line, we need to study, we need to see what this looks like in the pi eta twisted sector. And this pi just adds, it has an endpoint which changes the bosonic operator to a fermionic operator. So we find a twisted sector fermion, which is an R sector fermion. Similarly, if you start from the twisted sector in the initial bosonic theory, this can be thought of. This is understood as a fermion at the end of the pi p twist line. So it's a twisted sector charged operator which maps to a twisted sector charged operator. So it's an eta twisted, eta charged operator. And attaching a pi line just changes this fermion to a boson. So we end up with a R sector boson. These are the fermionization rules. And so to summarize, there are 4 theories that one can get by different kinds of gaugings. There's a Z2 gauging, which is just in the bosonic world, which maps sectors, essentially swaps charged and twisted sectors. And then we can fermionize this theory by stacking with R, gauging some diagonal of P and pi, and identifying the fermion parity to be pi eta. In doing so, we get a theory TF. Instead, if we had identified the fermion parity after gauging to be just eta instead of pi eta, you'd end up with T tilde F. And this orbit of theories is related by fermionization, gauging, stacking with R on this side. So R stacking just exchanges the R sector fermion with the R sector boson. And one can go diagonally. This is known as GSO projection. So some examples of fermionic symmetry categories. The simplest is just Z2F. Here, categorically, it's called the supervector spaces over Z2. And this is the product of SVec with vec Z2. The objects are just 1, P, and pi. P squares to the identity, bosonically, has the isomorphism to the identity, which is bosonic. Pi has a fermionic isomorphism to the identity. And there's a choice of fermion parity that one needs to make. You can either choose it to be P or pi P. And as we saw, it comes from the fermionization of a usual Z2 symmetry category. Next, we could look at SVec Z4. Here, the objects are generated by P and pi. P to the power 4 is bosonically isomorphic to the identity. Pi is fermionically isomorphic to the identity. And there are again two choices of fermion parity. One is P squared, the other is pi P squared. They're related by stacking an Apoorv. And they come from two different categories upon fermionization. So Z4F, which corresponds to the choice P squared, comes from vec Z4. So you can see that this local operator, here denoted in green, is a twisted sector operator of P squared. And after gauging, we saw that a twisted sector operator goes to a R sector boson. So that's just something that's attached to -1 to the F. And therefore, -1 to the F is P squared. While Z4 pi F comes from a category that has Z2 times Z2 symmetry with a mixed anomaly. This mixed anomaly essentially encodes that if you have a junction of two P lines, that junction, this green operator, is charged under P prime. Now, if we gauge P prime in the sense of if we fermionize using P prime, then this operator is a charged operator, and the charged operator goes to a charged twisted operator. So I could think of this as a fermion at the end of -1 to the F, or I could think of this as a boson at the end of pi times -1 to the F, which just implies that -1 to the F is pi P squared. So there are two ways to get Z4F kind of symmetry using two different categories that are Morita equivalent. And finally, I'll consider one, so I'll keep coming back to these three examples, Z2, Z4, and rep S3, fermionic versions of them. And so the way I present rep S3 is, so the way I present S3 is, has two generators, A and B. I'm going to call the order 3 generator A and the order 2 generator B. The objects in this fermionic category are 1 P E, which are in the usual rep S3 category. And there's a Cartesian product between 1 and pi, and so there are 6 objects. And the fusions are, these are just rep S3 fusions, and the rest of them can just be deduced using what I described earlier. There's a choice of fermion parity. Again, there are two choices. So there's a Z2 subsymmetry in rep S3, which is generated by P. We can use it to fermionize. We can use it to declare the fermion parity. So P could be -1 to the F, or P could be pi times -1 to the F. And from fermionization, the first choice comes from rep S3. So consider a fusion category rep S3 with, I'm now denoting P as P prime because I want to gauge this P prime and call something P on the other side. So there's a Z2 symmetry generated by P. This green operator is again in the twisted sector of this symmetry. It goes to the twisted or the R sector boson after fermionization. Therefore, we have -1 to the F appearing in the fusion product of E with itself. So I can identify this P with -1 to the F. in contrast, this second choice comes from Vec S3 instead of Rep S3. So we have a category where the lines are labeled by group elements of S3, and B swaps the line A with A squared. Therefore, and we want to fermionize using the Z2 generated by B. Doing so, A and A squared combine into a single operator, which I'm going to call E. And in particular, there's a charged operator, charged under B, at the junction of A plus A squared with itself. So if you take A squared plus A squared A, sorry, A squared minus A squared A, that's charged under B because A and A squared get swapped by B. And therefore, this purple operator is charged under B and it goes to the twisted charge sector. Therefore, it has a pi line attached to it. So are there any questions at this point about what I've described?
So are all these examples with some S vec box times standard bosonic fusion category?
Yes.
Any fermionic non-invertible symmetry is of that type?
I think that there can also be other kinds of symmetries that involve some anomalies that cannot be captured as just a box. Yeah. For
So
instance,
what's an example where it doesn't factor in this way?
Yeah. So one example would be Z2 times Z2F with an anomaly. These anomalies are classified by Z8. And
Right.
for instance, if you take the even one, so any even or 2 or 6 in 8 basically, then those correspond to symmetry categories where the Z2 generator squares to pi. So they don't factor.
Right. So it's like an extension almost.
Yes, you can think of it as an extension. And
Okay.
in terms of fermionization, it comes from a bosonic theory with an anomaly that is trivialized on a Z2. So if you take a Z4 bosonic category that has some H3 anomaly, but that H3 anomaly is trivial on the Z2 subgroup, you can then fermionize that.
Okay.
Yeah.
Right. Thanks.
So now I'll move on to describing symmetry TFTs for fermionic systems. And of course, in the last years, this has emerged as a very, very important method, and it's extremely powerful. This is a very partial list of references, but this is used for many things to study categorical symmetries. I should also say it's referred to using different names in different communities. In condensed matter, people usually call a symmetry TFT topological holography or symmetry TO, or sometimes categorical symmetry. And this has been used to systematically understand the representation theory or charges of a categorical symmetry. For classification of gap phases, understanding various kinds of gauging related dualities of quantum systems, and also universal properties of gapless phases and lattice models. So it's really a very economical and useful tool. I'm going to now purpose it for studying fermionic symmetries. So let me first recap how it works in the bosonic setup. So any S-symmetric theory T can be constructed as an interval compactification of the SIM-TFT with certain choices of boundary conditions. So there's a topological boundary here referred to as B sim S. And in particular, the fusion category of lines or topological defects on this topological boundary, the symmetry boundary, is the symmetry. So if one wants to study a theory with some symmetry operators inserted, that would correspond to studying the SIM-TFT setup with an insertion of some defect lines on the left boundary. The right boundary instead is what carries the dynamical non-universal properties of a theory that we want to study. And it is generically non-topological, but it is topological in some cases. And since the symmetry is localized on the left boundary, any operator that wants to talk to the symmetry structure must do so through the bulk, which is the symmetry TFT. Therefore, the organization of charges or representations is naturally implemented in terms of bulk topological operators. So let me describe the symmetry boundary. This is the symmetry boundary is topological, and it's specified in terms of a Lagrangian algebra, which essentially encodes the subcategory of lines, the subalgebra of lines that can end topologically on a boundary. So here NA are some integers, and A for any non-zero NA, A's have to satisfy some conditions. In particular, they have to be bosonic, so their topological spin has to be integer, and they have to be mutually local. And there's a condition of maximality, which is written here, which ensures that anything that's not condensed on the boundary is confined. And now this Lagrangian algebra also naturally describes the fusion category of lines, which is the symmetry, in the following way. One can take any bulk line and project it onto the boundary, and it either projects to the identity or something non-trivial. It may split into multiple simple lines on the boundary, and the structure of these projections is basically the symmetry. Generalized gaugings in this setup correspond to gauging an algebra inside the category of lines on the symmetry boundary. So if I want to study a theory where some subalgebra inside S has been gauged, it would involve inserting a fine enough mesh of these algebra lines on the symmetry boundary and then compactifying. And notably, this doesn't do anything to the SymTFT because this entire manipulation is only localized on the symmetry boundary. Therefore, theories that have gauge-related symmetry structures share the same symmetry TFT. And this symmetry TFT can be constructed using any of those symmetry structures. So, and this also includes twisted gaugings, like stacking of an SPT and then gauging and so on. Now, let's look at the symmetry TFT for fermionic symmetries. As I mentioned, I'm only going to be looking at symmetries that have a non-anomalous fermion parity, so they can always be bosonized. And since bosonization and fermionization are topological manipulations in the sense that they only swap sectors around, they don't provide any new dynamical information. They're in fact very analogous to gauging. Therefore, this kind of a manipulation can be done localized on the symmetry boundary. And therefore, the symmetry TFT for such fermionic symmetries is in fact bosonic. And it's the TFT that one gets from the symmetry category after bosonizing SF. The fermionicness can be localized on the symmetry boundary. So more precisely, a fermionic symmetry boundary is actually any bosonic boundary condition can also be thought of as a fermionic boundary condition with the fermion parity implemented by either the identity or the pi line. And this just amounts to taking any bosonic theory and viewing it as a fermionic theory in a trivial way, or just stacking the R theory on it and then viewing it as a fermionic theory. Something more non-trivial is when we use a genuinely fermionic boundary condition to define the fermionic boundary. And this means that at least one line in the bulk that is fermionic can end on the boundary. Any line that has at least a single line that has topological spin -1 is allowed to end on the boundary. So more precisely, we can define a fermionic Lagrangian algebra, and this Lagrangian algebra satisfies the same maximality condition as a bosonic algebra. The only difference is instead of only bosonic lines, one also allows a fermionic line to end on it. And all these lines have to still be mutually local. So the only one piece of information has been relaxed, which is we are allowing for fermionic lines. And you can either think of this as a fermionic Lagrangian in a modular tensor category, or as a bosonic Lagrangian algebra in a supermodular tensor category. So I could allow pi lines to also exist in the bulk. And then I take a fermion that I want to end on the boundary and just paste a pi line on it. this the end of the pi line is some local operator O pi, that's fermionic, and therefore this becomes a bosonic end, and I can use now the usual category, bosonic Lagrangian algebra with these pi f's instead of f's, and we'll usually be working with this kind of a convention. So let me describe the same examples that I described earlier, but in what kind of fermionic symmetries one can obtain from the SymTFT. So again, the simplest example, which was Z2F, the SymTFT for this is the toric code, because its bosonic dual is just an ordinary Z2 symmetry, and the toric code has these 4 lines, 1, E, M, and F. There's a single fermionic boundary condition, as there's a single fermion, and we just need 2 simple lines in here. And this is 1 plus pi f. So the bulk to boundary map, I can declare M to end as some line P, and therefore E must end as pi P, because EM or F must end as pi, because pi F is condensed on the boundary. So the F line becomes a pi line on the boundary, M becomes a Z2 or order 2 line P, E becomes pi P. And then there's a choice of fermion parity where one could choose either P or pi P, which means that the projections of either M or E implement the fermion parity symmetry on the symmetry boundary. The next example is Z4. So the SymTFT for this is the Z4, SymTFT for Vex Z4, which is Z4 Dicraft Witten. The lines, so I'm actually I use this notation Z of S both for the SymTFT and for the category or the Drinfeld center, the modular tensor category of lines in the bulk. The lines are generated by E and M, the pure charge and flux of the Z4 Dicraft Witten theory. They both are order 4 lines. And again, now there are 2 fermionic boundary conditions that are related by EM duality of the Z4 Dicraft Witten theory. I'll restrict to the first one, which is LF, without loss of generality. You can always get the second one by implementing an EM duality. And the bulk to boundary map for LF is as follows. So M ends on the boundary as an order 4 line, which is P. And since E ends the same way as pi P squared, pi M squared, using this Lagrangian algebra, E must become pi P squared on the boundary. There are again 2 choices of fermion parity, P squared and pi P squared, and these correspond to fermionizing 2 different boundaries of the Z4 Dicraft Witten theory. The first is LE, which is generated by E. And the second is LE squared M squared, which is generated by E squared and M squared. And this is compatible with the fact that the first choice came from fermionizing a Z4 symmetry. So this boundary actually carries a Z4 symmetry. However, the second choice of fermion parity, which is pi P squared, came from boson fermionizing some Z2 symmetry inside a symmetry category that has an anomalous Z2 times Z2 symmetry. And that's precisely the symmetry that this boundary carries. So therefore, these 2 are the bosonic duals of these 2 choices. And lastly, there's this rep S3F or rep S3 pi F symmetry, which is realized on the boundary of the rep S3 Dicraft Witten theory. This theory has 8 lines, one of which is fermionic. So we can define a fermionic boundary condition on the boundary of this theory. And there are 2 choices. I've just listed one here. This is the choice. And on the boundary, the symmetry category that we get has rep S3 symmetry tensored with S supervec. This is the rep S3 is generated by 1p pi, and then there's 1p in E, and then there's this pi line which comes from the S vec factor. And there are 2 choices again, P and pi P. Under bosonization, the choice, the first one, which is -1 to the F, realizes P, bosonizes to a boundary of the S3 Dirac-Witten theory, where all the fluxes have condensed. And a way to see this is if you take this boundary, which has -1 to the f implemented as p, and we see how the line A ends on it. It ends as 1 plus p. Therefore, the endpoint of this A line has two ends. The first end just is a topological local operator, and the second end is a p-twisted operator. In other words, what we have is an NS sector boson and an R sector boson. Now, upon bosonization, the NS sector boson becomes a local operator, and a R sector boson becomes a twisted sector operator of the dual Z2 symmetry. And these two ends are precisely the end of A on this boundary. So what one can do as a recipe, you take any line and see how it ends on the fermionic boundary, and bosonize those end line, the multiplet of operators one gets on the end of that line. Upon that bosonization, we'll find a new structure of operators, and that should be what is realized on the corresponding boundary by taking the same line and ending it. Yeah. So let me move on to describing generalized charges of fermionic symmetries. This is very similar to the bosonic case that was studied in several works. We follow the approach of Lakshya and Sakura. And the idea is that irreducible SF multiplets are, as a set, correspond to simple lines in the Drinfeld center or the SIM-TFT. So you can take some line in the SIM-TFT, and a multiplet is obtained by listing what possible topological ends it can have, and what twisted sector lines those ends implement. And the full set of these epsilons and y's give an irreducible multiplet corresponding to a bulk operator A. One can also study how symmetry acts on these multiplets by the linking action of some line on the symmetry boundary. And in particular, this linking action can implement a map from some twisted sector Y to another twisted sector Y prime, which is prescribed by specifying this local operator at the junction of X, Y, and Y prime. So by studying this full structure, one gets different SF multiplets, and this works for bosonic and fermionic symmetries in the same way. And so we work this out. I just give the same example. So if you look at Z2, the different lines in the Z2 SIM-TFT became these operators on the boundary, the symmetry operators, 1p, pi p, and pi. And if I consider the fermion parity to be implemented by the p line, then you can see that the M bulk line ends on a topological local operator that's a boson, but it's in the twisted sector of the fermion parity operator. So it's an R sector boson. However, the E line ends on a bosonic operator that's in the twisted sector of pi p. So I can think of it as a fermion parity twisted fermion. So it's an R sector fermion. Meanwhile, the fermionic line in the SIM-TFT ends on just the pi line, and the pi line can also be thought as an untwisted sector fermion. So it's an NS sector fermion. Similarly, for Z4, we saw that the E and M lines in the SIM-TFT end on pi p squared and p. So first, let's look at p. P is just the operator that generates the Z4 symmetry on the boundary. So one gets a p twisted sector boson, and this is uncharged under p because M doesn't link with, M has a trivial linking with itself. Meanwhile, the E line ends on, is in the pi p squared twisted sector. So we can think of it as a p squared twisted fermion because it's attached to this pi line. And in particular, this local end has a charge of I under the P symmetry. And this is just a consequence of the fact that the braiding between E and M is I. So these charges are reduced by the braidings, the bulk braidings of the lines, the different bulk lines with the M line, which generates the P symmetry on the boundary. And finally, the rep S3F symmetry on the boundary, we use this Lagrangian algebra. Let's consider the case where the fermion parity is generated by P. The boundary projections of these lines is listed here. And using similar compatibility conditions, one gets these multiplets of operators. So the P operator becomes a P-twisted sector boson. E becomes an E-twisted sector boson, or a boson that implements a local operator between the E and P lines. And similarly, the A and B lines in the bulk become these operators here, depicted here. So in the remaining time, let me move on to phases and transitions. So I'm going to be generalizing the recipe described in these nice papers here to fermionic systems. So phase is defined via a set of condensed charges, A in the Drinfeld center. And these charges have to be bosonic and mutually local. They have to be bosonic. So by condensed, I literally mean that in any theory, in any phase, these have a non-trivial vacuum expectation value. So they're condensed in a very conventional sense of the word. And they're bosonic because we require some kind of Lorentz invariant description of this theory. And therefore, only bosonic operators can condense. Further, they have to be mutually local because non-local operators can't simultaneously condense. So naturally, the physical requirements impose that we have to look at some condensable algebra in the Drinfeld center. And any charge, there's also these confined charges. So any charge that's non-local with respect to at least a single condensed charge is confined. And confined charges don't act within the low energy subspace because there's some energy penalty to creating excitations corresponding to these confined charges. Therefore, low energy subspace only has condensed charges and some other set of charges that I'm calling deconfined. These are charges that are local with respect to all condensed charges, and they generate gapless excitations. They may potentially generate gapless excitations within a phase. Everything here is modulo symmetry preserving deformations. So one can always deform away any statement made about gapped or gaplessness of a phase is up to this isomorphism. So the notion of a gapped phase is that there are no deconfined charges. Everything is either condensed or it's gapped out. And this defines a maximal condensable algebra, which is the Lagrangian algebra. And so what one has to do in the SymTFT setup is take a Lagrangian algebra and define the physical boundary using that. So both the physical and symmetry boundary are topological. Now the only difference is we'll consider a fermionic topological boundary on the symmetry boundary, and some general Lagrangian algebra, some bosonic Lagrangian algebra on the physical boundary. And as is the case for bosonic symmetries, the condensed charges on the physical boundary would give us the order parameters for this particular gapped phase. Gapless phases instead are defined using, they may have deconfined charges which provide the gapless excitations. In general, one can also have some gapless theory where all the gapless excitations are trivially charged under the symmetry. And in this case, one can always gap these out while preserving the symmetry. So symmetry imposed gaplessness is implemented by deconfined charges. And a set of deconfined, a condensable algebra which has deconfined charges, so not all charges are confined or condensed, is a non-maximal condensable algebra, A inside this SymTFT. And this implements an interface between the SymTFT and some smaller topological order. denoting here as Z prime. So what is the physical boundary that one can have? So we've defined this interface using some non-maximal condensable algebra. The question is, what is the physical boundary that one can have for defining a gapless phase? And there are various conditions that one requires from this boundary. The first is that there should be no topological local ends of any line inside this reduced topological order. This is just the condition that if there would be some additional objects that were condensed, and we're requiring maximal gaplessness. This can also be relaxed, but it's more if you have additional lines that are condensed, you could always just include them in the condensable algebra. There's a notion of completeness where there should be at least one non-topological end for each of the lines. So after compactifying, the theory that we find has all the charges, all the representations of the symmetry present. And there's irreducibility, which translates to the fact that there are no topological local operators here. If there were, we would get two decoupled theories, each labeled by some combination of topological local operators, and then we could just study these independently. So it makes sense to study irreducible gapless theories. And one can now take this setup with an interface inserted in the middle and absorb this condensable algebra either on the left. So if we absorb it on the left, it produces a potentially reducible topological boundary of Z prime, which decomposes into a sum of boundaries that they're all fermionic. They may or may not be all fermionic. And these lines form a multi-fusion pi supercategory with the constraint that the fermion parity implemented on the symmetry boundary is the sum of fermion parity implemented on all the individual summands or all the different components of this multi-fusion category. And using the SymTFT, we can deduce how the symmetry SF acts on this decomposable boundary. It's realized as a functor from SF to I'm calling the symmetry on this. I'm calling this multi-fusion category SF of BF prime. So this is a functor from SF to SF of BF prime. The way this is deduced is as follows. So firstly, there are some lines inside SF before compactifying, and those lift to some lines in the SymTFT. So I could take a certain line that, let's say, projects to a symmetry generator S and sandwich that line between the yellow and blue, the yellow boundary and blue interface. Upon that sandwich, we find some topological lines on this boundary that act within the symmetry category. So this gives us a functor from SF to SF of BF prime, or at least part of it. But there can also be topological local operators. In fact, there are if this decomposes. And these local operators correspond to topological lines that could be extended between the yellow and blue surfaces and can end on both. So if you take such a line and compactify it, it becomes a local operator. Let's call this local operator O. The linking of O with some symmetry lines on the boundary give us maps between different sectors of this multi-fusion category. And these two pieces of information completely specify how this SF symmetry is implemented on this boundary. Conversely, absorbing the interface to the right produces a SF symmetric gapless phase if you take an appropriate physical boundary on the right side. And so now one can ask about deformations of these gapless phases. We consider the case where everything that's been confined has order 1 penalty, energetic penalty, to be condensed. But there are many gapless excitations in this gapless phase that are captured by the set of deconfined charges. So one can deform infinitesimally such a theory by further condensing some subset of deconfined charges. And this structure was described in the paper I referred to earlier and forms a natural partial ordering in terms of inclusion of condensable algebras. So you can take something where nothing is condensed, everything is deconfined, and then sequentially gauge different subalgebras, condensable subalgebras, and form a hierarchy of deformations. And this forms a Hasse diagram. So using these methods, now we can study the phases and transitions in the different examples that I've been describing through this talk. The simplest is, again, is Z2 F symmetry. And this is the Hasse diagram. There's a single trivial condensable algebra that can be deformed into the two condensable algebras, which are 1 plus E and 1 plus M of this Z2 TFT, Z2 sim TFT. And in terms of phases, you can see that here the E line is condensed. So it carries an order parameter, which is an R sector fermion. This is the defining property of an R phase. Therefore, as a fermionic phase, this AE gap phase corresponds to the R theory. Meanwhile, AM, which carries order parameter M, has a bosonic operator in its fermion twisted sector, or the R sector. Therefore, this is a trivial theory. This is the defining property of a trivial theory. And we can also get this Hasse diagram from fermionizing the bosonic diagram. So if you take Z2 SSB, this has a local topological operator that's charged under Z2. And charged operators get mapped to R sector fermions. So you take that operator, it becomes a R sector fermion, and the existence of an R sector fermion implies R. And similarly, the trivial theory has a twisted sector topological operator, which maps to an R sector boson under fermionization. So you get a trivial theory. And the easing transition, which realizes which is the transition between these two Z2 gap phases, can be fermionized to the Majorana CFT. Now let's move on to the Z4 case. Here, the Hasse diagram is given here. There are three maximal condensable algebras or Lagrangian algebras that correspond to three gap phases. And then there are three non-maximal algebras that are that realize transitions between these gap phases. So let's look at, for instance, this one, which is generated by E squared. The reduced topological order is the toric code. And the symmetry boundary after slamming this interface implemented by this non-maximal algebra decomposes into two fermionic symmetries, BF1 plus BF2, which are both the fermionic boundaries of toric code. This has deformations to a Z2 ARF SSB phase, which has two vacua, both of which realize the ARF theory, and a Z2, a bosonic Z2 SSB, where there are just two vacua, both of which realize the trivial phase, the trivial fermionic phase. Instead, let's look at the easing, let's look at the algebra AM squared. This is, again, it implements an interface to toric code. And as a symmetry boundary, it realizes a bosonic symmetry. Therefore, this transition between Z2 SSB and Z2 and trivial is really a bosonic transition with the fermion parity symmetry implemented by the identity line. So this is a trivial, this sub part of the Hasse diagram is actually bosonic, but it's viewed as a fermionic. All these theories are viewed as fermionic. And finally, there's this SU2 level 1, which comes from the E squared M squared condensable algebra. The reduced topological order is double semyon, so it just has a single possible choice of boundary condition. This boundary condition also is bosonic. There's no fermionic boundary condition of the double semyon. And it admits a deformation to the symmetry broken phase, where you have two vacua, both of which realize the trivial fermionic theory. this Hasse diagram can be obtained by fermionizing the bosonic diagram. Let's look at some parts of it. So, for example, the Z4 SSB contains local operators that carry all charges of Z4, and we want to fermionize the Z2 subgroup of Z4. Therefore, it has a charge. There's a local operator that's topological and charged under that Z2 subgroup. Therefore, this theory goes into the R phase. In fact, there are two operators that give the two vacua, both of which are R's. Using similar arguments, one can just fermionize this entire diagram and get this the Hasse diagram on the fermionic side. Finally, let's look at the rep-S3F Hasse diagram. Here there are 4 condensable algebras, so 4 Lagrangian algebras. So there are 4 topological gap phases, and there are different transitions that can be realized between them that are implemented by non-maximal algebras. Let's look at the first one, which corresponds to this AE algebra. This implements an interface to toric code, or Z2 Dirac-Witten, with a symmetry boundary being fermionic. And here, this is the R phase, so the fermion parity is implemented by the pi line, while the E symmetry is implemented by 1 plus pi. The other deformation of this phase just is to the trivial phase, where both -1 to the F and E are implemented by the identity lines. I should say that this part of the Hasse diagram is also bosonic, because this boundary condition is actually a bosonic boundary condition. So these 3 phases here should be thought of as bosonic phases with fermionic phases, which are actually have an underlying bosonic phase where fermion parity acts trivially. The most interesting part is actually this part, where the symmetry boundary is a direct sum of a bosonic boundary and a fermionic boundary. And as a multifusion category, this also has Q-type lines, which are interfaces between these 2 components of this fusion category. The fermion parity is implemented as so there are 2 vacua in this gap phase. The fermion parity is implemented as the identity in the first vacua, whereas the pi line on the second vacua. So it's like trivial. The underlying theory is trivial plus R, viewed only from the perspective of fermion parity, while the E line is implemented in a more interesting way. So there's this on the 0th vacuum, it's implemented as a pi line. So it's the R theory, but there's this S line which goes between these 2, and this is a Q-type line. So it has this topological line has a local operator, an endomorphism of this line, which is fermionic, which can be seen by the fact that this S operator can absorb the pi line, which has a fermionic end. So this is the symmetry structure we get, and with that, this can also be obtained by just bosonizing. So you can get the bosonic Hasse diagram by bosonizing this, or conversely, you can fermionize the bosonic Hasse diagram that has this structure. So since my time is up, I should conclude. There are various future directions that would be interesting to pursue. Of course, there's higher dimensions where fermionic symmetries can be way more interesting. Not much is known about the structure of phases and even symmetry categories in this case. There's lattice realizations. There was some, in particular, the rep-S3 examples were realized on the lattice by fermionizing spin models with rep-S3 symmetry in this paper by Chatterjee, Aksoy, and Wen. Also, these systems with non-invertible fermionic symmetries may have interesting boundary phenomena. They might have some multiplet of Majorana 0 modes that realize some interesting action of a non-invertible symmetry. And this would be interesting to also think about. And then there are other directions relating to anomalous fermion parity symmetries and their SymTFTs and understanding transitions between them and phases. And finally, perhaps the most interesting is also to extend this to systems that are much more realistic from, say, a condensed matter point of view, some kind of extended Hubbard models that have also a U1 number conserving symmetry. And can there be non-invertible symmetries in these systems? How do they constrain the physics? So with that, thank you for your attention. Please let me know if there's some questions.
Okay, thanks very much for this nice talk. Other questions? Maybe I can ask, so do you have an example where you can't get it from the already known bosonic Hasse diagram, where you really sort of have to do the fermionic analysis?
You're asking whether there's any example that...
Yeah, whether you considered an example where you can't do this.
Yeah, so
sort of fermionization. Right, you could have just forgotten all you've done and just done the fermionization applied to all the known algebras and phase the whole Hasse phase diagram.
Yes, the phases could be obtained using fermionization, all of them, because everything that we always consider non-anomalous fermion parity.
So I guess my question is, have you considered anomalous ones, where you would have to do this analysis directly in the fermionic context?
Yeah,
it wouldn't be so a nice, shortcut.
So the answer is no, we haven't looked at anomalous fermion parity. Part of the reason is that those phases always appear as relative theory. So they have a gravitational anomaly. So you can't really, they can't support themselves. There's no lattice realization of those models. So they're perhaps less physical from that point of view. But but in a sense, they're theoretically maybe more interesting because they don't have a bosonic counterpart. That anomaly is really genuinely fermionic. Yeah.
Are there any other questions? Don't see any questions. Maybe we thank Apoorv again, and then I'll stop the recording. You should also stop yours.
Yes.
So is there some story about supersymmetry here? Like